Hello, my name is Devrat Tomar from EPFL. Thank you for your interest in our paper Test Time Self-Learning with Automatic Adversarial Augmentation. Test time adaptation, or TTA, refers to adapting a pre-trained model to a distributionally shifted unlabeled test domain, where access to the training dataset is restricted. Current TTA methods have several shortcomings, for example, outputting overconfident predictions leading to model calibration issues, dependency on architectures and training strategies, inconsistent performance across different types of distribution shifts, and limited applicability. Our method's main motivation is to simulate hard-to-classify images by using adversarial augmentations and adapting the model on those augmented views. Adversarial augmentations bring the feature representations of easy and hard images closer to the decision boundary, promoting learning from easy images while discarding updates on hard images. We achieve superior results on the classification and segmentation tasks for various distribution shifts, including common image corruption, synthetic to real, and measurement shifts of medical images. Our method is also agnostic to model architectures and source training strategies as shown in the bottom left figure, besides offering improved class-wise feature separability as shown in the bottom right figure. Our TTA framework has two parts. In part A, we propose a new test time objective which performs teacher-guided mutual information maximization. In part B, we perform knowledge distillation from the teacher to the student on automatic adversarial augmentations, which are learned simultaneously in an online manner. We propose flipped cross entropy as a proxy to teacher-guided mutual information maximization. The student model FS is adapted on the test images by minimizing the proposed test time objective LPL using the high-quality soft pseudo-labels obtained from the teacher model FT and pseudo-label refinement module PLR. In addition, we update the student model by using adversarially augmented views of the test images. This update is achieved by minimizing the KL divergence between the predictions made by the student model on those augmented views and the corresponding soft pseudo-labels provided by the teacher model. Our overall test time loss function is then defined as a combination of teacher-guided mutual information maximization and knowledge distillation on adversarial augmentations. We store the average teacher's predictions and the corresponding feature representations on weakly augmented views of test images in an online balanced queue. The refined pseudo-labels are then obtained through soft voting of k-nearest neighbors of the current test images from the online queue. The automatic adversarial augmentations are learned simultaneously while adapting the student model. We first define our augmentation policy search space and the loss for evaluating a specific augmentation policy, followed by proposing an efficient method to sample and learn optimal policies. A sub-policy row is defined as a combination of n image operations characterized by their magnitudes. Then, all possible sub-policies with their corresponding magnitudes constitute policy search space. We denote the magnitudes and probability of selecting sub-policies by M and P respectively. To evaluate a specific sub-policy row, we calculate the following loss term using the teacher model. A sub-policy is considered good if the output of the teacher model has high entropy when applied to the augmented views of the test images. To ensure that the augmentations are realistic, we also incorporate a regularizer term that measures the distance between the feature statistics of the augmented view and the original view of the test images without augmentation. Finally, we minimize the expected policy loss with respect to the probability of selecting a sub-policy and its magnitude using an unbiased gradient estimator. The first term of the gradient estimator optimizes the magnitude of the sample sub-policy ρi, while the second term optimizes the probability of selecting the same sub-policy in the future. We performed several ablation studies to study the effect of individual components of our method, including sensitivity to hyperparameters for the two test time evaluation protocols corresponding to online evaluation and O, that is one epoch, and offline evaluation and M, that is multiple epochs. Here, we see the benefit of using flipped cross entropy in place of normal cross entropy as a test time objective, which is further improved by the proposed LPL for both TTA protocols. In this ablation, we show the effect of including the pseudo-label refinement module on the final average class accuracies for both protocols. We see the best improvement by combining the teacher's average prediction on weak augmentations of the current test image with the nearest neighbor soft voting using online Q. In this ablation, we show the contribution of individual components of our proposed test time objective, including teacher-guided mutual information maximization, pseudo-label refinement, and knowledge distillation on adversarial augmentations. We also show that our method is robust to change in the batch size of the input test images as well as the learning rate used for updating the model. In summary, we propose a novel self-learning TTA method utilizing efficient automatic adversarial augmentations. Our method is agnostic to model architectures and source training strategies. Also, our method achieves superior performance on different types of test time distribution shifts, including image corruption to measurement shifts in medical imaging. One limitation of our method is that it assumes test time images are class-wise independent and identically distributed, which will be addressed in us future work. Thank you for watching this video. Please visit our project page for more details.